Hello, and welcome to another video lecture for ME372 Machine Design. In this lecture, we are going to talk about axially symmetric problems, or axisymmetric problems. You'll note that in the pictures here, we have several applications of these types of problems. An axisymmetric problem is defined as one where you can rotate around the axis and the loading and the geometry does not change. In these top two pictures, we see two pressure vessels that have failed. This is a scuba tank that has failed, and this is a large water tank that failed. And you can see here that in this failure, the crack is longitudinal, and we have the same crack in this pressure vessel over here. You'll note, or you should remember and understand that this is not by chance, but the stresses that cause these failures are called the circumferential stress, and they tend to open up the crack in this direction. And for thin-walled pressure vessels like these here, this circumferential stress is twice the radial stress. So when pressure vessels fail, they will always fail with a longitudinal crack like this that has been generated by a sigma theta, or a circumferential stress. We also see down here several applications of cylindrical geometries. Here is a submarine going through a jump, and if you ever get the chance to ride in a submarine and do this, or even if you get to ride in a submarine simulator and go through a simulated jump, it is a cool feeling. The forces and the acceleration that you feel are huge. You might think submarines are kind of slow and you don't feel much of a G loading, but when you go through a jump and jump up out of the water, the forces that you feel are really big, and it's just a lot of fun. It's a fun ride. This also shows that there are applications of axisymmetric problems in submarines, in missiles. Here's another missile. And then if we look at all the cylindrical geometry that is in this fighter plane, we have the fuselage, we have this missile, we have our jet engines, and several cylindrical shapes make up this fighter plane. So it's important as an engineer that we understand the stresses and strains that develop in these axisymmetric type problems. And so we're going to spend the next 2 days talking about axisymmetric problems. To begin with, let's give again a definition of axisymmetric. And actually symmetric problems occur where the structure is unchanged if rotated around an axis. And when it says where the structure is unchanged, this means the loading and the geometry. The basic definitions of the stresses are given in terms of polar coordinates as shown below. So here we're looking down the axis, the longitudinal axis of a cylinder. This is the cross section of a thick-walled cylinder. So it would be like taking this pressure vessel and cutting it through in this direction here and looking down the axis. In this case, we've labeled the x-axis to the right and the y-axis going down. The radial direction starts at the center of the cylinder and goes in a radial direction outward. When we have stress in this direction, we call it simply the radial stress, and we give it the symbol sigma r. Now, acting down along the axis, so into the page, is sigma z, and we call sigma z the longitudinal or the axial stress, and we give it the symbol sigma z, and again it would be acting into the page. The other stress shown here is sigma theta, and sigma theta acts perpendicular to the radial direction. So here I'm showing this element as finite, and so the sigma theta would be perpendicular to that plane and perpendicular to this plane. If this were a differential element, the sigma thetas would essentially be in opposite directions. I'm showing here a tau theta r, where the tau theta r is the tau on the theta plane and in the r direction. And this is a shear stress, and it's simply called tau theta r or the shear stress. Other names are not given or typically used. It's important to note that in this configuration with sigma r and sigma theta and sigma z, there is no shear stress. Sigma r, sigma theta, and sigma z are the principal stresses. And so I've shown tau theta r here because if you were to rotate these directions, you would have these shear stresses develop. But in these actual directions, tau theta r would be 0. So a couple important points to note about axisymmetric problems is that sigma theta is always larger than sigma r and has its maximum at the inside radius of the system independent of the loading. So from that statement, we learn that sigma theta is always the critical stress. Now we often want to look at the combined effect and look at sigma theta, sigma r, and sigma z, as we have learned in the previous section on failure theories. It's important to look at the complete stress state. But sigma theta will be the largest of these stresses if sigma z is open, if we have an open-ended cylinder. So I guess to be clear, sigma theta will always be larger than sigma r, but this longitudinal stress can become a very large stress as well and can actually become larger than a sigma theta. But in terms of the axisymmetric stresses, sigma theta will always be greater than sigma r. Sigma z can become large. Sigma theta here has several names. Sigma theta is often called the hoop stress, the tangential stress, or the circumferential stress, or just sigma theta. So it's the same stress and it's computed with the same equations, but it is given several names. Again, sigma theta, the hoop stress, the circumferential stress, and the tangential stress. The radial stress is only known as the radial stress. The sigma z is known as the longitudinal or axial stress. Coming to our next note, we see that sigma r is the stress that provides the boundary conditions used to solve the differential equation governing the stress. And we'll see what I mean by this in the next few slides. This stress is always equal to the negative of the pressure on the boundary. What that means is that on the inside surface here, the radial stress is always equal to the negative of the inside pressure. And on the outside surface, sigma r is always equal to the negative of the external pressure. Sigma z here is 0 if there aren't end caps on the cylindrical vessel. Something like a hose where there's just flow through it and there aren't any end caps, then sigma z can be 0. If there are end caps where we now have a closed pressure vessel, then sigma z can become a significant stress. And this sigma z is like an axial stress. It's like a P over A type of axial stress. And we'll look at the equations for that on the following slides. On this slide, we show here the expression that governs the stresses in a cylindrical element or cylindrical axial stress type problem. This expression here is derived from equilibrium and compatibility equations. And compatibility equations are what force displacements to be equal. We see that in this system we are solving for phi, and phi is the Airy stress function. We can see here that we take a second order partial derivative of phi with respect to r, but we also have an operator over here. We see that this partial squared operates on this quantity here. So actually what we have is a fourth order partial differential equation. We note that it is only a function of r. So the solution to this fourth order partial differential equation will have 4 constants of integration that need to be determined from boundary conditions. Note that we don't have any time involved in this expression, so we don't have temporal conditions, but we have boundary conditions. The solution for phi from this equation has been derived and is given by a ln of r plus br squared ln of r plus cr squared plus d. Now this has changed from your notes, so make sure your notes reflect this expression. A, B, C, and D are the constants of integration that we need to solve for. Now, for the stresses in a cylinder, the radial stress is defined as the partial of phi with respect to r multiplied by 1 over r. So to get the radial stress, we need to take the partial derivative of this expression here with respect to r and then divide by r. Doing that gives us this expression here. The sigma theta, the hoop stress, is defined as the second partial derivative of phi with respect to r squared. This second order partial derivative results in minus a over r squared plus b3 plus 2ln of r plus 2c. The shear stress again is 0 because we are looking at sigma theta and r, which are the principal stresses. Now, to carry on with the derivation of the expressions for sigma r and sigma theta, we discard the b terms to make the displacements single valued. And what this means is we know that our displacements always need to have only one value. For a given loading condition, you can't have 2 different values for the displacement. So we discard the b terms. The c term gives an isotropic stress field, and we keep that term. The a term equals 0 for bodies without a center hole, but in our cylindrical problems, we're interested with bodies that do have a center hole, and so we will have the a term there. So the expressions that we end up getting are sigma r is a over r squared plus 2c, and sigma theta is minus a over r squared plus 2c. And again, A and C now are determined from boundary conditions. The thing that's really important to note here is that the only difference between the radial and the circumferential stresses is this minus sign. And it seems a little counterintuitive that the minus sign down here actually results in a larger stress. But that's indeed what happens. So the minus sign goes on the sigma theta, and it actually creates a larger stress than the plus sign does up here on sigma r. Now, the boundary conditions that we're going to use to determine A and C are both set on the radial stress like we talked about before. The boundary conditions on the radial stress that we will set are that the radial stress is equal to the negative of the pressure. So over here at sigma r, at r equals b, where b represents this outside radius and a represents the inside radius. Now some textbooks will use ri here and ro here. So don't let that confuse you. Ri is simply equal to A, and we'll use A as the inside radius and B as the outside radius. So coming over here, the radial stress at R equals B is equal to the negative of the external pressure, PO. And the other boundary condition is sigma R at R equals A at the inside surface is equal to a negative of the internal pressure, minus Pi. Now we have two equations and two unknowns. The two unknowns are A and C. Subtracting equation 1 from equation 2 and rearranging lets us solve for A, and A turns out to be A squared B squared times the quantity Pi minus PO over A squared minus B squared. So we now have the A term here, and we can solve equation 1 for 2C and get that 2C is equal to this expression here. Now, rearranging and plugging these components into the expressions for sigma r and sigma theta, we get that sigma r is pi a squared minus po b squared all over b squared minus a squared plus 1 over r squared times a squared b squared minus pi plus po over b squared minus a squared. And again, we note that the only difference between sigma r and sigma theta is this minus sign. So to review this expression, A is the inside radius, Pi is the internal pressure, PO is the external pressure, B is the external radius, R here is the point of interest. So if we wanted to compute the stresses throughout the wall of the cylinder, little r here would range from A to B. Little r takes on the value at the point of interest, or the point where you're wanting to compute the stresses. And usually we look at the stresses at the inside of the cylinder, where this little r would be A, or we look at the stresses on the outside of the cylinder, where this little r would be B. But it could be anywhere in between. Down here on the sigma z equation, this term right here represents the axial load in the material. So this is essentially the force over the area type of expression for the axial part. Again, Pi is the internal pressure, PO is the external pressure. And this is the axial stress due to an end cap on the end of the cylinder. This P over pi times quantity B squared minus A squared is a little misleading. This P right here is not a pressure. And so the symbol for P there is not a very good use of a symbol when we're using pressures in all of these other locations. But P without the subscript is commonly used, and it represents an externally applied force. So for example, if you had this cylinder and you had a hook on the end of this cylinder and you were pulling on that hook, that's what this P would be. This P would represent, this P would represent that externally applied end force. So this is not a pressure. This is an external force that would be applied pulling on or pushing on the end cap, and this would be a radius area type of term down here. So these expressions right here are the governing expressions for the stresses. In terms of what you need to know, I will give you on the exam one of these equations, but I will not give you the other equation. And so you need to realize that these equations, the only difference between them is what we want to look at now is how these stresses are distributed throughout the wall of the cylinder. So coming to this next slide, what we're going to do is we're going to let the internal pressure in this cylinder be greater than 0, and we're going to let the external pressure be equal to 0. And we're going to compute the stress distributions throughout the wall of the cylinder. So essentially, the game that we play is we write down the governing equation for the stress, and then we simply plug in the appropriate values. So here I have a PI that's greater than 0, so it goes in as a positive value. I've let my PO equal 0, so I'm putting a 0 in as a placeholder there. My point of interest is going to vary from R equals A to R equals B. So putting in these zeros and simplifying this expression, I get this expression here. Now we ought to be able to check our boundary conditions and make sure that this equation here satisfies our boundary conditions. And so we know that at R equal to A, which would be at the inside surface, this expression here better equal negative PI. So if I put in A squared here, I have 1 minus B squared over A squared. And this reduces to negative PI because what I would do is I'd get a common denominator here and write this 1 as A squared over A squared. And then this A squared minus B squared would cancel with this B squared minus A squared and give me a minus sign. I'd be left with an A squared in the denominator down here that would cancel with this A squared, and it would leave me with a negative PI. If my radius is equal to B, I would have B squared over B squared, which would be 1. 1 minus 1 would give me 0. And so this shows that I have done the simplification right, and my boundary conditions are satisfied. Now if we look at the sigma theta stress, we can see that we get a minus sign here, which results over here in a plus sign. So now when I put in A, I can see that I'm going to have 1 plus B squared over A squared. And that quantity will always be larger than when I look at it at the outside surface, where R squared would be equal to B squared. That would be 1 plus 1, where when I look at it at the inside surface, this quantity will be greater than 1. So the stress distribution through my cylinder looks like what is shown here. This quantity, 1 plus B squared over R squared, will always be bigger than 1 minus B squared over R squared. B's and R's are squared in their geometry values. So this quantity here will always be larger than this, which tells me that my sigma theta is the critical stress. So my sigma theta will always have a larger value than the radial stress. We can see here that the circumferential stress does not go to 0 out here on the free end, but my radial stress does go to 0. And so the key takeaways from this example are that first, the game that we essentially play is to write down the expression for sigma r or sigma theta and then solve for the unknown. And we may be solving for the stress at a particular point, or we could have a design situation where we know the maximum allowable stress and we want to solve for the internal pressure. Then we could solve this equation to help us determine the internal pressure. But we essentially have one equation for sigma r and one equation for sigma theta, and so those are the unknowns that we can have. Then the key takeaway is that sigma theta is always largest on the inside surface of the cylinder, and that makes it hard for inspection systems. If the stress is largest on the inside, then that's where our system will fail first, and it's hard to detect cracks on the inside and failure starting to initiate on the inside of the cylinder than it would be to detect failure on the outside of the cylinder where we can easily visualize it and see it. So key things to remember are sigma theta is always largest on the inside surface of the cylinder, and that's independent of loading. If we let PO be greater than 0 and PI be equal to 0, we would still get sigma theta largest on this inside surface. So sigma theta will always be the critical stress, and it's always critical on the inside surface of the cylinder. Now let's look at an example problem. In this example problem, it says we have a cylinder that has an outside diameter of 0.3 meters and an inside diameter of 0.2 meters. So it's a fairly thick-walled cylinder. The cylinder is subjected to an external pressure of 140 MPa. The longitudinal stress is 0. What is the maximum shear stress, and at what radius does it occur? So we just talked about how sigma r and sigma theta are principal stresses, but we can change the orientation that we're looking at those principal stresses and find a shear stress. And so what we want to do is we want to find the maximum difference between the principal stresses. And that will give us the largest Mohr circle. And the largest Mohr circle will have the largest radius, which then gives us essentially the largest shear stress. So what I have done is I have written MATLAB code where I first clear all other terms. I define PO as, or PI as the internal pressure, and it's a 0. PO I've defined as 140 e to the 6th. My inside radius is 0.3 divided by 2, and my outside radius is 0.3 divided by 2. My inside radius is 0.2 divided by 2. And then I let R range from A to B in increments of 0.001. And then I compute sigma R and sigma T, and I plot them. And so here's a plot of sigma R, and here is a plot of sigma theta. And again, we note that sigma theta is by far the largest at the inside wall. We see that our radial stress meets our internal pressure of 0 boundary condition. And what we want to do now is determine the maximum distance between these two curves. And we see that that distance occurs here at the inside wall. So what I want to do is plot a stress element where I have this radial stress and this circumferential stress. Doing that gives me a stress element that looks like this. I have a zero radial stress, so a stress going up in this direction would represent the radial stress, but at zero, I compute my circumferential stress at that point to be 504, and it's negative, so it's shown in compression. So what I have is this stress element, and I need to find out the maximum shear for that stress element. So I come down and I take my vertical point, and I get minus 504, 0, because I have a minus 504 here, and the shear stress is 0. My horizontal point is sigma y, which is 0, comma tau xy, which is 0. So I plot my vertical point and my horizontal point. This becomes my origin of planes, my OP. My maximum shear will occur on a 45-degree angle coming up to this peak. And that's because my origin of planes here is at the 0 tau location. And so for a circle, if you're at this horizontal point, the angle to the peak is 45 degrees. And I know that the radius of my circle is simply half of this 504. So the center of this Mohr circle would be at minus 252 and 0, which gives the radius of 252. Therefore, the maximum shear stress occurs at a 45-degree angle from the horizontal and on the inside wall of the cylinder, and has a magnitude of 252 megapascals. So I hope this gives you an example of how to use the cylindrical stress equations and solve these axisymmetric problems. We will continue this discussion in the next lecture by looking at press fits and what happens when we combine multiple cylinders that are pressed together. But for now, make sure you can understand this example and understand these governing equations here for the stress